Hi guys, welcome to the mini lecture on calorimetry. So calorimetry literally means a measurement of heat. Calor is a Latin word for heat. So in this mini lecture, we're going to explore some experimental techniques for measuring energy transfer processes for a variety of chemical and physical applications. Okay, so let's throw out an explicit definition to kick things off here. So calorimetry is essentially a technique for measuring the heat, and remember, heat is an energy transfer process that's associated with some sort of physical or chemical change. Okay, and so we typically use the letter Q to represent energy. Okay, and we're basically just saying, okay, let's quantify that energy that's associated with some sort of change. So, for example, if you are heating up water, okay, so heating up water is obviously involving some sort of energy transfer where, for example, if you're using a gas burner here, that gas burner is going to be pumping thermal energy into that water, right? That water sitting there in the kettle. And we know that as Q increases, if we put more Q, more thermal energy into that system, then there is going to be a corresponding increase in the temperature, right? The water is going to continue to heat up until ultimately it starts boiling. Okay, so we have this proportionality. So what we want to do now is, in order to be able to come up with a more precise mathematical relationship, rather than just explore the proportionality, we're going to introduce the concept of heat capacity. So heat capacity is defined as the quantity of heat required to change the temperature of a substance by 1 Kelvin. Okay? And we're typically, when we're talking about heat capacity, we're going to use an uppercase C to denote the heat capacity. And the expression for the heat capacity is going to be Q over delta T. So building off of the relationship in the previous slide, we could also write this as Q equals C delta T. So this capital C heat capacity is serving as our constant of proportionality. Now, this is an extensive property, okay? The more substance you have, the greater the heat capacity. In other words, right, if you have twice as much of the substance, well, then you're going to need, and you put a certain amount of energy in there, you're not going to see as significant of a change in the temperature. So let's look at an example. So let's suppose that the heat capacity of some substance is 2.1 joules per Kelvin. How much energy is required to increase the temperature of that substance by 10.0 degrees Celsius? So the first thing I want to draw your attention to is the units that we're using. Notice from equation 1 here, we are defining the heat capacity as an energy over temperature. So joules over Kelvin is our chosen units on this problem, okay? And what we're effectively needing to do is figuring out how much energy is required to carry out a certain change. So we're going to rearrange equation 1 to solve for Q, and we are then going to take the given values. In this case, C is 2.1 joules per Kelvin, and T, the delta T, is 10 degrees Celsius. And remember that 1 degree Celsius is equal to 1 Kelvin. Okay, there's a shift, but there's no scaling factor, right? 1 degree Celsius is equal to 1 Kelvin, so I'm just going to do a direct conversion here so that my units of Kelvin cancel out, and we can arrive at the final answer. Okay, so heat capacity represents a nice, simple, and intuitive quantitative description describing the relationship between energy transfer and the temperature, the change in temperature of the system. Okay, now let's build on this a little bit. Okay, let's suppose that we want to be able to compare the thermal properties of two different materials. Well, it would be convenient then if we could come up with some sort of comparison that essentially nails down the amount of substance that you have. Because it wouldn't be fair to compare the heat capacity of 20 kilograms of aluminum and 1 gram of water, right? Because it's such a vast difference in the amount of substance. And that heat capacity being an extensive quantity obviously depends on how much of the substance you have. So to remedy that issue, we're going to define what we call the specific heat capacity, oftentimes just called the specific heat, and we're going to denote this guy by a lowercase c. And I apologize, this lowercase c will show up again later, speed of light, for those of you taking other classes. Don't get confused. It should always be clear from context. If you're talking thermochem, then when you see a lowercase c, you should think specific heat capacity. So the specific heat capacity is the amount of heat required to change the temperature of 1 gram of substance by 1 Kelvin, right? So not just to change the temperature by 1 Kelvin, but to change the temperature of a fixed amount, 1 gram of the substance. So by nailing down the amount, we have effectively formed an intensive property that will be a fundamental characteristic of a given material in question, right? Then following the same sort of work that we saw in equation 1, we can then write out an expression right here, equation number 2, that relates the total energy, Q, okay, total energy required to raise a certain mass of substance, M, by a certain temperature change, right? And of course, this amount of energy will depend on the unique thermochemical properties of the substance in question, and those are going to be captured by our specific heat term here, which is of course our lowercase c. All right, so let's jump into an example of using this Q equals mc delta T equation. A lot of folks will refer to that as the MCAT equation. So the example problem here is giving us a layer of copper that's welded to the bottom of a skillet, and it's telling us the mass of this copper, 125 grams. And we want to determine how much heat is needed to raise the temperature of the copper from 25 degrees Celsius all the way up to 300 degrees Celsius. And we're given, in the context of the problem, the specific heat of copper. Okay, so we're of course going to be using the MCAT equation, which requires a delta T. Mass is given for us, but all we're given here is a final and initial temperature. So our first step is going to then be to determine what sort of temperature change we're dealing with. In this case, it's going to be 275 Kelvin. And of course, it's going to be a positive value because we are heating up that copper welded to the bottom of that skillet. Then we're going to plug in that 275 Kelvin right there into equation 2. And then plug in the values for the mass, 125 grams. We saw that before, right up there. Then we're going to plug in the given value for our specific heat of copper. And then the delta T that we just found in step 1. Pay close attention to those units. Grams on the units of that specific heat of copper, right, are going to cancel out with the mass, the given mass. The temperature in Kelvin is going to cancel out right here. And once again, I did a direct conversion, from that delta T from Celsius to Kelvin. And the final answer you will arrive at then is 1.33 times 10 to the 4th joules. Okay, so now that we see how to work with these concepts of heat capacity and specific heat, we're now ready to start answering the key question of this section, which is, how can we take these thermodynamic measurements, in a laboratory setting? All right, so the first technique we're going to talk about is so-called constant pressure calorimetry, right? So for processes that take place at constant pressure, the heat transferred, right, which is denoted Q, and we're going to put a little subscript P to denote that we're under a constant pressure scenario. is often measured using a device called a coffee cup calorimeter, which can actually be constructed out of a coffee cup. So the idea behind a coffee cup calorimeter is, we want to provide some sort of thermal isolation, right? Which is, the styrofoam cup going all the way around here. So what we're effectively doing by having a styrofoam cup and then with a nice lid on the top is we are providing a thermal barrier so that whatever sorts of energy transfer processes that are occurring inside the container in here, where for example we have some reaction mixture or some physical transformation, whatever it might be, whatever's happening in there, okay, will be thermally isolated from the surroundings. In other words, we're not going to be gaining heat from the surroundings, right? There's not going to be any heat coming in, right? And we're not going to see any heat coming out. Furthermore, by using a nice big bath here of water, right? Water, as we'll see as we're working through some more example problems, later on, water has a relatively high specific heat. And so what is oftentimes happens, or the typical setup, I should say, for a coffee cup calorimeter is to carry out some sort of reaction here, and we want to figure out what is that Q associated with that reaction. And we're going to measure that Q by essentially measuring what the Q is for the water inside of this calorimeter, right? And because the Q inside, because the water and the reaction are both contained and thermally isolated inside of this calorimeter, we know that the Q for water, right, all the energy that is transferred to the water or away from the water is all either coming from or going into the reaction. In other words, the magnitude of QH2O, the Q of the water, is going to be equal and opposite sign to Q reaction. Okay. I've said that a little bit backwards there. The magnitude is going to be equivalent for both of them, and the actual QH2O is going to be negative Q of reaction. Right. Whatever one gives up, the other one grabs. Okay, so to make sense of this and get a feel for what we can do, let's look at a simple example where you have a heated chunk of solid, right? In this case, it's a 22.0 gram solid, and we've heated it up in a test tube, rather high temperature, all the way up to 100 degrees Celsius, and we add this now heated metal sample to 50 grams of water in this coffee cup calorimeter. Right? And we watch that temperature. Remember that on that slide we have at the top here we've got a temperature thermometer, so we can monitor the temperature as the process progresses. And through taking those temperature measurements, we find that the water changes from 25.10 degrees Celsius all the way up to 28.49 degrees Celsius. And our goal here then is to find the specific heat capacity of that solid. So the heat lost by the metal, right? Because we know that the metal is hot and it's cooling off, it's transferring energy to the water. Okay, so if we have a little picture going on here, we've got some water here, we've got a little piece of metal, and that little piece of metal is giving off energy. Okay, but because that energy transfer process is occurring in a calorimeter, it's thermally isolated from the surroundings, so all of that energy lost by the metal is showing up in the water. Right? So then, if we monitor the changes in temperature of both the water and the metal, right, and we go back to the problem and say, okay, well, we know they're both ending up at the same final temperature because we're looking at thermal equilibration. And we subtract off their initials. So remember, the water was room temperature, the metal was initially nice and hot. We get the corresponding delta T's, and notice the delta T for the metal is negative because it was cooling off. Okay, and once we have the delta T's and we know the masses for each one of these substances. We know 50 grams of water, and we know the mass of the metal. We can re-express our equation up here using the MCAT formula, right? So Q metal is going to become M metal, C metal, delta T metal. QH2O is going to become MH2O, CH2O, and delta TH2O. Now all we have to do then is solve for that unknown, the C metal, heat capacity of the metal, and then plug in all these given values. Because we know the identity of water, we can look up the specific heat of water. Okay? In this case, the specific heat of water is 4.184 joules per gram per degree Celsius. Right? So if we follow again through, make sure that all of our units are working out, this Celsius is going to cancel, right? We have our delta T, grams are going to cancel here. The units that are going to be left are just going to be the same units that we reported our heat capacity of water in. So you carry out the math and you'll get something like 0.450 joules per gram degree Celsius. And as I said, a minute ago, we'll notice that oftentimes water will have a significantly higher heat capacity than the metals, right? And so a lot of the metal examples we'll see, they'll oftentimes be on the order of an order of magnitude lower heat capacity, or specific heat rather. Okay, so that's the basics of a coffee cup calorimeter. So this is obviously a process carried out at constant pressure. And as we move forward, we're going to revisit this example in the coming lecture videos when we're starting to examine chemical reactions. We'll see that a lot of chemical reactions actually take place under constant pressure conditions. So we'll come back to this example. For right now, I want to take a second and look at the other flavor of calorimetry, so-called constant volume calorimetry. So in constant volume, this is not something you could carry out in a styrofoam cup. In fact, it's constant volume calorimetry is carried out in a device known as a bomb calorimeter. So the bomb calorimeter has a very tough and strongly built outer shell that provides thermal insulation as well as a significant degree of structural support to ensure that the volume of the substance undergoing a change is in fact held constant. So one of the typical problems that is solved using a constant volume calorimetry is to figure out the heat of combustion of various substances. So the idea is to take whatever substance under investigation and put it inside this chamber, and then make sure you've got plenty of oxygen, enough oxygen to ensure you can fully react in a standard combustion equation, all of that sample that you place in there. Put in an ignition coil to make sure that you can get the conditions intense enough to cause all of that substance to become combustible, or to combust rather. And once that sample is fully combusted, then of course you're going to be getting some products, right? And you're going to be releasing a lot of thermal energy. And all that thermal energy, because of the thermal insulation in orange here on the outside, will remain inside of that calorimeter. And then if during the course of a separate experiment, the heat capacity of that calorimeter, you can monitor the change of that calorimeter, the change in temperature, and then figure out how much energy must have been released by that sample that you combusted. So to see an example of this, let's suppose we have a question here where you have a dessert, right? So a dessert that you could eat, and it's claimed to have fewer than 10 calories, okay? So a calorie here with a capital C, these are the calories that you see listed on the back of your food containers. Okay, so this is a new unit we're going to have to pay attention to. So 10 calories, but just like joules, it is a unit of energy. Okay, and a single serving of this dessert then that's claimed to have fewer than 10 calories is placed inside a bomb calorimeter and burned. Right? You make sure you have plenty of O2 in there and you're going to burn the whole dessert. And then you find that the initial temperature of that calorimeter is 21.862 degrees Celsius. And after burning all of your dessert, the calorimeter jumps up to 26.799 degrees Celsius. If the heat capacity of the calorimeter is 8.151 kilojoules, note the kilojoules there, per Kelvin. Is this claim correct? All right, so we have to evaluate whether or not we're going to be under that 10 calorie limit. So first off, I'd like you guys to go ahead and try and solve this problem. Try and think through it before I walk you through it. And pause the video. All right, so the first step when we are solving this problem is, of course, to realize that we're dealing with a calorimeter. And so it's thermally isolated. So all of the energy that comes out of that dessert is going to end up in that calorimeter. Okay? And we're going to make this assumption, just like we did with the coffee cup, that there is no heat lost to the surroundings. Okay? And so the temperature change of the calorimeter is given to us in the problem by carrying out our subtraction. And we're going to see it's just under 5 degrees Celsius. Okay? And so all we need to do then is go back to equation 1, which tells us that Q equals C delta T. The specific heat, all right, the amount of energy that is absorbed or released is directly related to temperature. All you have to do is multiply by this constant, the heat capacity. We know the heat capacity from this experiment and from the experimental setup here. We know we're given a calorimeter that has 8.151 kilojoules per degree Celsius as a heat capacity. We'll then multiply that by the temperature, right? And then we will come up with a final answer here. Now, paying close attention to those units, we have units of kilojoules. So 40.24 kilojoules of energy is released. So then the question is that less than 10 calories? Okay. So in order to carry out that last step, we're going to have to convert these uppercase calories that we talked about when we're looking at food stuff into a unit that we can compare with kilojoules. So it turns out that one uppercase calorie that we use on food containers is equal to 1 kcal, 1 kilocalorie, lowercase calorie. And 1 kcal is equal to 4.184 kilojoules. Therefore, 10 calories is going to be equal to 41.84 kilojoules. So our value of 40 is obviously less than 41.8, so the claim is correct. All right, so those are the two main calorimetry techniques, the ones that you need to know for the course. Now you should go ahead and work through a handful of example problems exploring the different ways that we can use both the bomb calorimeter and coffee cup calorimeter to answer different questions. After that, we are going to move into our final topic of discussion for the thermochemistry discussion series, which is that of enthalpy. And now we're going to start bringing in chemical reactions and talking about enthalpies of reactions. So stay tuned for that. But remember, before you move on, work through those practice questions.